we're going to talk about the central limit theorem today. So most population distributions are actually not normal. What we talked about yesterday was if the population distribution is normal, what do we know about the sampling distribution? It's normal. Okay, so yay, it's kind of easy if they tell you the population's normal. If it's not normal, we're going to talk about that. And again, most population distributions are not normal. For example, the household incomes that we looked at the other day, this first one is the population distribution. And notice it's skewed right because of those really rich people. Okay, so this guy skewed right. However, what happens to our sampling distribution? This one's our sampling distribution. What does that look like? Looks normal. Why is that? So let's look at these. What's the shape of the sampling distribution when the population distribution isn't normal? So we're going to look at this activity on page 453, if you guys would find in your book page 453. Oh, that's good. And I'll just put my email up there for everyone to see. There we go. So back to this guy. And we're going to follow through on this activity. Zach, will you read number 1? Is this the same one as yesterday? Yeah, go to the next one, you guys.
Oh, snap.
That's weird. Yeah, so whatever. That's the previous one, sorry. So it's on page 456. 456. Thanks.
Go through that 10 months after. The bottom two graphs display the 1%.
Oh wait, hold on, I'm not ready. Sorry, my thing didn't work. Alright, so we're going to go skewed right. And what else? Or skewed?
Set the bottom two graphs display the 1% size 2, the other is 5.
Cool, okay.
Click the animated button a few times to be sure you see what's happening.
Alright, so what happened, you guys? The first two, that's just the pure number you got, and the next one is the average of those two, right? So this is the sample data, like maybe it's a bunch of different salaries, our household incomes. This is 2 different household incomes, and we averaged it right there. All right, Zach.
Clear lower 3.
Okay. So if we take a sample of size 2, what happens? What kind of distribution do we have for the sampling distribution of the means? It's still skewed, okay? All right, Zach, keep going. All right, Adem, what's 2 say? Wait, I can't hear you. I'm really deaf. Thanks. 10, 16, and let's do 10,000. What's happening to our graph? Getting a little more normal. Okay. Oh, and what's the next thing? I don't know why we're not getting another. Thanks. I was like, this isn't working. Cool. 20, 25. So what's happening? Getting more normal. All right. So we're going to find that there's a cutoff here. Is there anything else we need to do? Summarize what you learned. All right. So the bigger the n, right, the bigger the sample size, the more normal, even with a skewed population. Okay? Even with a skewed population. So when the sample size is large enough, the sampling distribution of the population, or of that, is very close to normal. This is true no matter what shape the population distribution has, as long as the population has a finite standard deviation. All right. So this is called the central limit theorem, which you should write down. Draw a simple random sample of size n from any population with mean mu and finite standard deviation sigma. The central limit theorem, CLT, says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. Approximately normal. Okay? No matter what the population is, as long as we are taking a large enough sample, then the sampling distribution of the mean, so the average of all the little x bars, will be approximately normal. So if we had done n equals 5 with our penny activity, it probably wouldn't be big enough if we had a skewed population. 25 maybe, okay? But we're going to talk about the magic number here in a minute. All right. We use the sampling distribution applet to create a population distribution with a very strange shape. See the graph at the top of the next page. The figure below shows the approximate sampling distribution of the sample mean x bar. So that graph at the top of 458, if you guys see that, is pretty crazy looking, right? So it's not anything close to normal. We've got like 3 different peaks. Okay, next page. You got a really weird population. So what we did with the applet is we have n equals, 2, n equals 5, n equals 10, n equals 25. So of course what's happening as n increases? More normal, just like we talked about, okay? So there's a huge difference between taking a sample size of 2 and taking a sample size of 25. So this is the large sample condition for sample means. So if the population distribution is normal, then so is the sampling distribution of x bar. This is true no matter what the sample size n is. So the problem's going to have to tell you the population's normal, and then it doesn't matter what n is. You can go ahead and assume that your sampling distribution is normal, okay? But the second part, here's the magic number, okay? If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar will be, this is important, approximately normal in most cases of n is greater than or equal to 30. You need to write that down. That's the magic number right there, 30. As long as you're taking samples of size 30, doesn't matter what the population distribution is, you can say that it's approximately normal, okay, according to the central limit theorem. I know. So you do need to prove it. So remember when we're doing proportions, what's our formula to say if something is normal or not? N times p greater than or equal to 10, n times 1 minus p greater than or equal to 10. So that's for p's, right? For the x bars, you just have to say it's greater than 30. Even easier. So you're like, oh, I'm taking a sample greater than 30. I'm good to go, even if it didn't tell me that the population was normal. Central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations, even when the population distribution isn't normal. That was the whole point of that. All right, just a little summary right there of what we just learned. Let's try a problem. Okay, servicing air conditioners, calculations using the CLT. So your company has a contract to perform preventative maintenance on thousands of air conditioning units in a large city. Based on service records from the past year, the time and hours that a technician requires to complete the work follows a strongly right-skewed distribution, right-skewed, not normal, okay, with mean of 1 hour and standard deviation of 1 hour. In the coming week, your company will service a simple random sample of 70 air conditioning units in the city. You plan to budget an average of 1.1 hours per unit for a technician to complete the work. Will this be enough time? What's the probability that the average maintenance time x bar for 70 units exceeds 1.1 hours? Show your work. Okay. So what we're trying to find, and some of you guys didn't write this on your thing from yesterday, always say the probability that you're trying to find. And for this part, we're talking about x bar because it's our samples. So we want to know how often it's going to be greater than 1.1 hours, right? That's the probability that we're trying to find. We do have to state the sampling distribution. So the sampling distribution of the sample mean time x bar spent working on 70 units. So we're going to look at that. We got to find the mean and the standard deviation. So the mean should be pretty easy. So Tyler, what will the mean of all the little x bars in our sample be? Yep, the same as the true mean. Is equal to the true mean, which is equal to 1. Okay? And then we've got our standard deviation. But before we do our standard deviation, Jet, what do we have to check? Yeah, the 10% condition to see if it's met, right? 10% condition. So let's see, we've got 70 units. So what do you guys think? 70 times 10, multiply your sample by 10, that's 700, which is definitely less than all the units in the city, right? Units in the large city, all right? They specified that. Now we can go ahead and use the formula for standard deviation of sample means. So Owen, what's the formula? Good. So the true standard deviation, or the original one here for the population standard deviation, is 1. And we're dividing by the square root of 70 because our sample size was 70, and that gives us 0.12 hours. Okay. Then we want to use our normal conditions, but we need to check the normal conditions. So if we were doing proportions, we would do the NP greater than or equal to 10, n times 1 minus p. But for this one, we do the one we just learned, right? And so it is approximately normal. We need to say that, right? So we can say it's approximately normal, our distribution. Oops. Normal. All right. Because n is equal to 70, which is greater than 30. Okay, that's how they write it a lot of times. Okay, your sample is equal to 70, which is greater than that magic number of 30 that you want to memorize, and actually greater than or equal to. So we're good to go, and we can follow the normal condition. So now we can say therefore, the distribution of x bar is approximately normal. You can do that capital N, 1, 0.12. So we always write normal, mean, then standard deviation like that. So we can draw a little graph to find our probability. Again, I'm trying to find x bar greater than 1.1. And if we drew the normal curve based on 1 being the mean and 0.12 would be 1.12 above the mean, right? That's one standard deviation right there. So we're about here and to the right. There's that probability we're trying to find. Okay? And I was going to ask, I'm not sure how often you need to draw this graph, okay? But I drew it for you guys in this. I don't know how much that's required on the test or not, but there you go. I'm going to ask about that. Okay, and then we've got our normal calculations. Okay, so lower, Adem, what's our lower bound going to be? And upper, Donovan, is, we'll do 10,000 or whatever, okay? And our mean is 1, and our new standard deviation is 0.12. Plug that in, and you get 0.2023. And then always answer the question, you guys. You don't need to watch me write this out, but when we answer the question, if you budget 1.1 hours per unit, there's about a 20% chance that the technicians will not complete the work within that amount of time, right? 20% chance. So you get to decide, if you own the company, if it's worth the risk, taking that 20% chance. I don't know.